I want to start by acknowledging my brilliant collaborators, who are all here, actually. I have some things to tell you about that I think are really exciting, and I would not have any of it, especially without Evan, who's looking for postdocs, by the way, and also without Wilbur, Agnes, and Bowen. And here's some references. Two of these are still work in progress. I will mostly talk about the first two, and I maybe will say, if there's some time, just a little bit about the third. So there are many reasons to be interested in fractons. And here are three that each, I think, represent an important perspective on the topic that's also represented within the UQM collaboration. And this talk is largely going to take a condensed matter physics point of view, and I'll be talking about fracton matter as a new class of phases that are beyond our existing paradigms in condensed matter physics. And I won't have time to elaborate on it today, but really getting a feeling for what's fundamentally new about fracton matter is actually something that comes from thinking about the interplay between these three perspectives. So the interplay between quantum information, quantum field theory, and condensed matter viewpoints. It's something that's been really important to develop my own thinking about this subject. And in large part, that's been through collaborations and discussions with people in this room. And it never would have happened without the UQM collaboration, I think. So let's begin with a key example, kind of the hydrogen atom of fracton physics, the X-cube model from our chair's PhD work. This is a model where you put qubits on the edges of a simple cubic lattice. The Hamiltonian is a sum of commuting terms, each of which is a product of either X or Z Pauli operators. Hamiltonians like that are called CSS Pauli codes. So, and terms in the Hamiltonian are called stabilizers. So there are cube stabilizers that are products of X's, and three kinds of vertex stabilizers that are products of 4Z's on the edges next to a site. And correspondingly, there are two kinds of excitations: vertex excitations, where you excite the vertex stabilizers, and cube excitations. And what we're interested in is the mobility properties of these excitations. So that's what's unusual. So if you look at the vertex excitations, you can take one of them and move it along a line by acting with an X operator. But if you try to make it move along a line a little bit and then turn a corner, you have to leave behind another excitation. So these excitations are what we call line-ons because they're actually only free to move along a 1D line in the lattice. What if we look at a cube excitation? Well, if you try to take this cube and move it over to the right, what you find is that there's absolutely no way to do that without creating other excitations somewhere else. And this has the consequence that an isolated one of these excitations cannot move, okay, without creating other excitations. Excitations like this are what we call fractons, and they give their name to the whole topic. The X-cube model has other kinds of excitations with different restricted mobility. If you take two of these cube excitations and put them together, you get an excitation that can move in an XY plane. Similarly with two line-ons, and excitations like this are called plane-ons. Okay, so now let's back up a little bit. I want to give an explanation of what I mean more generally when I say fracton matter. Okay, so first of all, we're talking about zero temperature equilibrium systems, translation invariant lattice Hamiltonians, and the Hamiltonian should be local throughout the talk. Okay? And what do I mean by fracton matter? It means there's at least one gapped restricted mobility excitation above the ground state. And I want to give a definition of that. Okay? So in order to give a definition of that, we have to talk about the notion of superselection sectors, also called particle types or topological charges sometimes. And these are equivalence classes of point-like excitations above the ground state, where two excitations are equivalent if one can be transformed into the other by acting with some local operator. Okay? And there's a trivial particle type, which is just all of the excitations that you can make locally out of the ground state. And any particle that has a non-trivial type, that's what we call a fractional excitation, like anyon excitations, as, for example, Michael was discussing in his talk. Then what we want to do is we'll assume translation symmetry in order to talk about the mobility of these excitations. So naively, this has some disadvantages, but later in the talk, I'll explain to you how these disadvantages can be avoided. And I'll say what the disadvantages are, but not yet. So what do? So we can take an excitation and act on it with a translation by some distance. So translation is a non-local operator, and it can change the type of an excitation, but it doesn't have to. So we can ask if acting on this excitation with translation changes the type, or it doesn't. If it doesn't, then that means that we can find a local hopping operator, which has exactly the same effect on that action as the translation. And so that's like a dynamics term that we could add to the Hamiltonian if we want, that's going to move the excitation in that direction. If the type changes, there's no hopping operator that moves it in that particular distance. And so for any excitation, so let's say we're in d dimensions, the translation symmetry group on the lattice is z to the d. For any point-like excitation, there's a subgroup of translations that doesn't change the type. This subgroup is always isomorphic to z to the m, and we say that f has restricted mobility if this exponent m is less than d. So let me illustrate that a little bit in 3 dimensions, like for the x-cubed model. So I've listed all the possibilities for the group that leaves the type of an excitation invariant here. There are only these possibilities. And these are the names that we gave the corresponding excitation. The x-cubed model doesn't have any excitations like this, except the trivial one, excitations that are fully mobile in space. Planons always have a group that doesn't change their type isomorphic to z squared, and so on. For fractons, this group is trivial. Now, one thing I want to emphasize is that this group, you might say, well, is this all to the story of restricted mobility that this is? You just say what this group is for each restricted mobility excitation. The answer is no. It's far from a full description, but it is an important property. OK, so some further assumptions just to kind of lay out the ground rules of what I want to talk about and what I don't want to talk about. So I want to consider systems with an energy gap to all excitations. We'll consider systems that only have point-like excitations, so there will be no loops, like, for example, in the 3D toric code. I will not be talking about systems like that. The only symmetry that I'll impose is lattice translation, and that's going to play a special role, which I'll discuss later. And to keep it simple, we'll always talk about bosonic systems with a tensor product Hilbert space. Mostly I'll be in 3 spatial dimensions. And a very important assumption is that we'll talk about abelian systems. So that's a property of the superselection sectors. So what it means for a system to be abelian is that if you take 2 excitations and fuse them, the type of the composite only depends on the types of the constituents. So you get a unique binary, you get a well-defined binary operation on the set of superselection sectors S, which makes it into an abelian group. Okay, and the addition is what we call fusion. And in fracton systems, in contrast to anyon systems, this abelian group is infinite, and usually it's not even finitely generated. So it's a very big object. And we'll get to some more description of that later. OK, so yes. I'm always on an infinite lattice. Thanks for asking. Yeah. OK, so I gave you one example of a fracton model, but there are actually many, many examples. So let me just tell you about one other very briefly. So this is another CSS Pauli code called Haas cubic code. It actually predates the x-cubed model. And this is something called a type 2 fracton model because all of its non-trivial excitations are fractons. Whereas we call the x-cubed model type 1 because in addition to fractons, it has some linons and planons, which are partially mobile. And within Pauli codes, even within CSS Pauli codes, there are many other examples. Okay, but these are not the only examples. And in fact, there's now a vast landscape of many examples of fracton models, many families of constructions, different ways of constructing them. And I'm not going to tell you about all of these. A lot of interesting work done in many cases by people in this room, coming up with many fascinating examples. Okay, and so where we are now is kind of here. So this is the Fracton landscape, which you might also recognize as Bryce Canyon. And all these examples, they make up this apparently very complicated landscape. And, and in response to this, or as the examples were being developed, we also, as a community, came up with quite a few ideas that turned out to be important, many of those from people in this room. However, the state of the field, especially a couple years ago, although I think now this is changing, is that there were very few organizing principles to kind of make sense of this landscape. And actually, I'm reminded about a conversation that I had with Mike Zolotel a long time ago, actually early on when I was starting to think about fractons. And he asked me if I thought fractons are beautiful or ugly. And at the time, I really didn't know, and that's what I told him. And I had some other reasons for being interested in it at the time. But now I'm actually quite confident that fractons are beautiful. And we're starting, and it's taken us a long time maybe to find their underlying beauty. And the reason that we're doing that is we're starting to learn how to navigate this fracton landscape. Okay, so what do we need to do that? Well, the first thing we need is a notion of phases, okay, which I'll have to say a little bit about. So those are equivalence classes of quantum systems. And once we talk about phases, well, we need universal properties, exactly as Michael was discussing in his talk, just properties that are constant within a phase. In this talk, I'll call them phase invariants usually, but it's exactly the same thing. And something that's very important, which we actually don't think about a lot when we think about anyon models, is that it's really crucial for these universal properties to be something that's easy to compare between two different systems, like an integer or a finite group, small finite group, something like that. The reason this is important in fractons is that the mathematical structures that arise, as you'll see, are kind of big objects, and they're not easy to compare directly. So this ease of comparability is something really important, and it's not something that I think I appreciated was key until recently, okay? So I'll call this activity characterization, finding universal properties. There's something else we can do, classification, by which I mean an enumeration, really a list of all possible distinct phases with some specified characteristics. And it's really important to emphasize that these are not the same thing. Even though sometimes in our field these words are used interchangeably, they're really different, and you need both. So having this without that is not the best, because a classification doesn't necessarily come with a way to tell two systems apart. Having characterization without classification also is not the end of the story, because you don't know that you've found all the possibilities. Okay, so some comments on kind of the current state of things, or just a few remarks. So I kind of alluded to this, but it's actually tricky to define fracton phases, or phases in fracton systems. And I think I know what I would call the quote-unquote correct way of doing this. And I've given whole talks about this, actually. You can see an earlier one, somewhat out of date now, but it has a lot of the ideas. I'll explain what I mean by this in a simple and more concrete context, okay? Okay, another important point is that, recently we have started to come up with more easily comparable phase invariants. There's also a very nice one in some earlier work of Wilbur Shirley, Kevin Slagle, and Xie Chen that I didn't refer to here, but I should have. But I won't have time to talk about this recent work, also with people who are here in the room. And another thing I'd say is I'm not actually sure, though correct me if I'm missing something, that any subset of fracton phases has really been classified. I don't think there's an example of that, and I'm going to tell you about some, which I think are the first examples. They're pretty simple subsets, but they're not so simple that they're uninteresting. Okay, so before I tell you about our recent results along these lines, there's one other important idea I want to mention. It's one of the important lines of thinking that various people came up with as relevant to this subject. That's the notion of subsystem symmetry. Okay, so What is a subsystem symmetry? Well, these are symmetries that act on certain rigid subsets of our d-dimensional lattice, like lattice planes or lines. They can even act on fractals. And and these symmetries we've learned, again, I think we first learned in some work of our chair and others that there are important connections between these symmetries and Fracton phases. And one of the connections is that if you start, for example, with a trivial gapped state with a discrete subsystem symmetry, and you gauge the symmetry, that often results in a Fracton system. Okay. Another point is that subsystem symmetries, we learned as time went on, are interesting in their own right. They can protect non-trivial ground states, which we call SSPT phases. They're just SPT phases of subsystem symmetry. Okay? And there's another connection, which is that Fracton phases also have emergent low-energy subsystem symmetries, and these symmetries at least partially characterize Fracton phases. So you might ask, doesn't this greatly simplify the Fracton landscape? Because thinking in terms of symmetry is a powerful tool, and it is. But the answer is no, okay? It doesn't. A better answer is, at least not yet. And the reason why, which I think is something underappreciated, and I'm going to make this point in this talk, I hope, is that subsystem symmetries themselves are actually quite complex, and more complex than I think have really been appreciated. And they're not easy to compare between different systems. So it's actually a non-trivial problem, just like characterizing and classifying phases, to characterize and classify distinct subsystem symmetries. And it's important to note, I'm not talking about SSPT phases, I'm talking about just the symmetries. So even the symmetries themselves, there's a lot to learn about what types exist. And so it may be true, when we understand this problem a little better, I really don't think this problem has been appreciated until now, but once we understand it more, this program might be easier than characterizing and classifying Fracton phases. But right now, progress understanding this problem and the problem of characterizing and classifying phases is proceeding in parallel and in a way that's very closely tied together. So progress on this problem informs progress on the other side and vice versa. And so I'll illustrate this point in a simple setting later in the talk, but kind of the bottom line is that there's another landscape, the subsystem symmetry landscape, and it's closely related. So this is also Bryce Canyon, but before it snowed. So maybe gauging is the snow. Okay, but again, it's a complicated landscape, which I think is beautiful, but I would not have been so sure a long time ago. So here's the outline of the rest of the talk. I guess I should first say, just in general, what approach we will take. So rather than focusing on ground state properties, although I think you could translate this probably into a ground state story, we're going to focus on the restricted mobility excitations, which are kind of the defining property of Fracton phases. Okay. Actually, I forgot to say something really important, which is that the definition of a Fracton phase is there's at least one restricted mobility excitation. Okay. So what we'll do is develop an algebraic theory of those excitations above the ground state for certain types of Fracton orders. And once we've done that, then we'll characterize and classify the resulting algebraic structures. So the aim here, in terms of like I always feel in theoretical physics, it's an important skill to be able to tune the amount of rigor that you're using to different levels. So the level of rigor in the first part, developing the theory of excitations, is not that high. I'm not proving quantum statistical mechanics theorems. But the aim is for the level of rigor in the second part, characterizing and classifying these algebraic structures, to be mathematical rigor with no caveats. Okay? And the reason for that, I think that's really the approach one should take, because these are mathematical structures that we're not used to. And in fact, it's even it's been very hard for us to even find results about many of these in the math literature, and so we've had to invent many things for ourselves. That doesn't mean it's not out there somewhere, but it's very hard to find if it is, and maybe not in a useful form. And the point is that the problem is very well defined once the first step is done, and there's sort of no real excuse to make a mistake. We should just get the answer right, so we should try to be rigorous. Okay, so what I'll start with is a little bit more background on what we're trying to do. I'll explain that more, say something about what we know the form of this algebraic theory should look like. Then I'll move on to a simpler subset of Fracton orders where all the excitations are planons. And then I'll tell you about some results classifying and characterizing those, as well as some related subsystem symmetries. If there's time, which I think is unlikely, I will tell you about something called the excitation detector principle, which Ashwin alluded to in his talk, which is an extension of the principle of remote detectability that plays a very important role in this whole story. And there's some cool results on mutual statistics in pretty general Pauli codes. We'll see if we actually get there. So in some sense, what we're trying to do is generalize a very familiar theory, the algebraic theory of abelian anyons in 2D. Okay, I'm not talking about unitary modular tensor categories because when we have just abelian anyons, we don't need the full power and complexity of UMTCs. There's a simpler theory, which is enough and equivalent, which is the following. So a theory of abelian anyons is a pair of a finite abelian group A and a quadratic form, which is a function from A to rationals mod Z that satisfies some properties. And the elements of A are anyons, they're superselection sectors. The group operation is fusion, and what does theta mean? It's the topological spin of an excitation. Something you might know from the theory of anyons is that actually if you know the topological spin, you also know the mutual statistics, B of xy. And it's part of the definition of a quadratic form that this function is bilinear in x and y. So it's bilinear by definition. Okay, so now there's a piece of universal data that we know is important in 2D gap phases, the chiral central charge, which Michael also mentioned in his talk. It's partially determined by this data, but not completely. But our philosophy is to focus on the excitations. And so we don't worry about keeping track of the chiral central charge. Okay, we're only interested in those properties we can extract from the fusion and braiding of the excitations in a direct way. Okay. So there's a very important condition on this algebraic data, which has different names. So this quadratic form should be non-degenerate. Sometimes this is also called modularity or braiding non-degeneracy. And it's just the statement that if you have a non-trivial enyon, there's some other enyon that has non-zero braiding with it. Okay? And this comes from a well-known physics principle, which is the principle of remote detectability, which I've phrased in this way, different ways of phrasing it. Any non-trivial excitation can be detected with some operator acting very far away from the original excitation. And in this case, that other operator is just the string operator of our other enyon that we're braiding around. Okay, all right? We know in this case that this condition, modularity, non-degeneracy, is actually a necessary and sufficient condition for such a theory, A theta, to be physically realizable. Okay, and that's, in order to have a good algebraic theory, that's a property we want. We want every instance of our theory to be something that you can make in a real system. How do we know that in this case? Well, there's a multi-component U1 Chern-Simons theory that can realize any of these A thetas. Okay, there's more to say about this, but that's enough for today. And so what we want to do is think about extending this to abelian Fracton orders where there's a key additional ingredient that we need, and that's mobility, okay, this restricted mobility. So we still have an abelian group of superselection sectors. Now we'll call it S. And let me just introduce an important quantity as an aside. So we'll define the fusion order of S to be the smallest positive integer that annihilates all of the excitations in S. We'll usually call it n. So that means that if you take any excitation and you fuse it with itself n times, you get the trivial excitation. So actually, this quantity can be infinite, and there are examples of Fracton orders where the fusion order is infinite that are really interesting and kind of weird, actually. But we're going to focus on the case of finite fusion order. And then what we're going to do, as I said, is we're going to use translation symmetry to incorporate mobility into our theory. So here's a place where I have to start introducing some mathematical language, and maybe it's a good place to make a remark. In this topic, there's some mathematical language from commutative and homological algebra, a lot of which came into the field through work of Ha, but also through work of others, that's I think is really essential to understand things in general, like characterization and classification. And it's really unfamiliar for most people in our field. And I also won't have time to explain everything as I go, but I think I've kept this language to kind of a minimum in this talk. And what I would say is any example can be understood without using this mathematical language. But it really is the right language to understand anything in general. And it's the sort of flavor that if you don't use this nice language, then you're making your life harder than it needs to be. Things become very cumbersome. Dan has a question. S is the set of superselection sectors, equivalence classes of particles. That was defined earlier. So two excitations are equivalent if they can be transformed into one another by a local operator. And in an abelian system, by definition, S is an abelian group. Doesn't have to be finite. And in Fracton systems, it's not. It's never finite in Fracton systems. Leo.
It's a simple example that in the X-cube model, you take a Fracton and you move it, and you transform it to three Fractons at a different location, right? By acting by
So that one Fracton and the three Fractons, those are in the same superselection sector. Because they have to be, because you can transform those two things into each other locally. However, a Fracton at a given position, x, y, z, and a Fracton at some other position, x prime, y prime, z prime, in the X-cube model are always in different superselection sectors, and you can prove that.
In the first example, those are two different elements of S? The three Fractons and one Fracton?
No, they're actually the same element of S. Different excitations, but they're equivalent, so they correspond to the same element of S. Yeah, Vadim.
To restrict the mobility, I'm allowed to think of all these things as degenerate eigenstates. Whenever you say three,
no, I'm not making any statement about the energy spectrum here.
Okay,
actually,
but it's not.
They're all gapped. But I'm not making any statement about what's an eigenstate, what's not. These are point-like excitations. So the states are ones where all the energy density and all the non-trivial observables are concentrated within some ball. And if you go far away from the ball, your local density matrices look like the ground state. They need not be eigenstates. In a generic system, an excitation like that never will be, because the eigenstates will be plane waves.
Right. But because this is why I thought that all of these things are restricted mobility, so they're localized, so there's no energy.
But a planon has some mobility.
Okay. Yeah. All right. Thanks.
Yeah. Good. Okay. Marcus. Then I'm going to move on because I have things I want to get to, as I warned you. I don't know. I don't know. Yeah, it is. Yeah, he also computes this group S for the toric code in his work. Okay. At least in that setting it is. I don't know if in higher dimensions in Fracton models it's the same thing. We should talk about it later. Yeah. Okay, so anyway, back to this mathematical language, right? So in 3 dimensions, our translation symmetry, let's take it to be z cubed. The important point is the translation symmetry acts on S, right? You can take an excitation, translate it, ask what type you have. So there's an action of z cubed on S. And a nice way to think about that mathematically is that that action makes S into a module over this Laurent polynomial ring in 3 variables, t1, t2, t3, with zn coefficients. Okay, so what does this mean? So the important point is that this monomial represents a lattice translation. So for example, T1 represents translation in the one direction. T2 represents translation in the two direction, and so on. Okay, an important point is that there are no infinite sums allowed here. So these are finite Laurent polynomials. It wouldn't be a ring otherwise. You have to be able to multiply these things. And just a reminder, in case it's not familiar to you, so what's a module over a ring? It's just an abelian group on which the ring acts via scalar multiplication. It's just a generalization of a vector space over a field. Okay. Physically, it's just that translation is acting on S. Okay, and this R module S, it's been known actually for quite a while, even going back to work of Ha in 2012. This R module S encodes both fusion and mobility properties of excitations. But that's not the full theory. What we really want, like in the theory of abelian anyons, is something like a pair of S and some statistical data, which I will schematically call theta, but in general, we don't know what it is, okay? We do know that there are interesting and very non-trivial generalizations of self and mutual statistics, even to completely immobile fractons. So for example, it makes sense to take two fractons and exchange them and ask what phase you get, even though they can't move in a completely conventional way. Right? A fracton can still move, but you have to create other excitations. So rather than a restricted mobility, which is the term we usually use, it might be better to say something like cooperative mobility. So there is some mobility, but it's complicated, and it's enough to define analogs of statistics. But we don't know how to give a full description of that statistical data in some nice algebraic way, okay? Or we haven't known. Actually, we now have an answer to this problem, in I think rather general Pauli codes, and I probably won't have time to get to it, but I'll flash it at least at the end of the talk. Yeah?
You need the mutual statistic. In anyons, you don't need it. You just need the quadratic.
Yeah, I think you should have something from which you can get the mutual statistics, at least, because the mutual statistics is what encodes remote detectability, and that's really a fundamental property. So that is the necessary condition for physical realizability. It's a necessary and sufficient condition for physical realizability in the anyon case. So that information needs to be somehow obtainable from this theory, right? You need to be able to check if the principle of remote detectability is satisfied. And so some kind of analog of mutual statistics, I think, is what you need.
I'm assuming it's redundant.
Oh, yeah. So I think that, right, that may be true, but we don't know in general. Of course, in anyons, we know that self-statistics is enough, as I said earlier. Yeah. So just an aside, I mentioned the fusion order. Later, you'll see me restricting to a theory with prime power fusion order, where n is a power of some prime. And the reason is that if n is a composite number, which is a product of many prime powers, you can actually make arguments that the theory should decompose as a stack of theories with prime power fusion order, and you can prove that in specific settings. Okay. So that's something you'll see me do as we go ahead. So, okay. So now I want to talk about a case that where we can actually easily make progress, but there's a little bit of a twist to the story. And this is the case of planon-only fracton orders, where all the excitations are planons that move in a stack of parallel lattice planes in three-dimensional space. Okay. Why can we easily make some progress here? Well, the statistics data is obvious, because statistics of planons is just like in two dimensions. Okay? There's just the same mutual statistics and self-statistics. All right? And so we know the data, the algebraic data of a theory. It's a pair of S and theta, and now we know what theta is. It's just a quadratic form that gives the topological spin. So in this case, we just specify the self-statistics. And we'll fix a fusion order n. It's also true that in this case with fusion order n, you can check the mutual statistics. You can think of it as taking values in Zn. So of course, there are a lot of really boring examples here. You just take any 2D abelian anyon state, and you make a lattice of it, and you have decoupled layers. and kind of who cares about that. But there's a very important example, and two of the authors are here at this meeting, which they called something else, but I'm going to name it after the authors, because this example turns out to be really important, and it needs a name. And I'm going to call it the Shirley-Slagle-Chen theory, or SSC theory. And so what is this example? So I'll tell you how it was originally constructed. Okay? They did this for Z4 but in their original paper, but I'll do it for ZP squared. So we'll choose a prime P. We'll start with layers of ZP squared toric codes. Okay? And in each layer, we have kind of generating particles, E's and M's, which I'll put tildes on. Those are just the electric and magnetic excitations of the ZP squared toric code. They have mutual statistics in the same layer with a 1 over P squared. Okay? And what we do from this decoupled layer state is that we'll condense interlayer of composites like in this picture. So P copies of Mi tilde in this layer, this should be EI minus 1, and P copies of minus EI minus 1 in the layer below. So this connects the two layers. And what they showed is that this gives a new theory where the fusion module S, set of superselection sectors, is generated by some excitations that we'll now call M and E. And these excitations have interesting fusion, which is expressed in this picture. So P copies of an E is always 0, but P copies of an M actually splits into two E's, one in the layer above, one in the layer below. Okay, so this looks interesting. And it's actually also known from earlier work in this paper, maybe elsewhere too, that this theory is not decoupled layers, and they saw this in some way, which I won't describe in detail. It's written on the slide. We'll see this in a different way in just a little bit. Okay, so there are interesting examples that are not just decoupled layers. So why not study these planon-only fracton orders? Okay, so there are some obvious. So we have this algebraic data. So then the question is, what are the conditions on the data? So there's some obvious conditions. Okay, we don't care about translations transverse to the stacking direction because all the particles are mobile in that direction. We only care about the normal translation, and that makes our ring of Laurent polynomials just a one variable polynomial ring. We're just keeping track of normal translation, which is represented by T. And the quadratic form has to satisfy two obvious properties. It has to be non-degenerate, so that's just braiding non-degeneracy again. And it also has to satisfy a spatial locality property. So if you take two excitations, x and y, and if you keep translating y, eventually you'll translate it far enough away that the mutual statistics has to be 0. It doesn't have to be 0 right away as soon as you get to the next layer, because the layers could talk to each other a little bit. But at some point, it's going to have to be 0. And so that's another condition. All right. So it's kind of important, actually, to talk a little bit about how this information should be packaged mathematically. And in particular, it turns out to be important to focus on the mutual statistics, which plays a bigger role in the theory in many ways. I guess one thing I'll mention is that if the fusion order is odd, it's also true that self-statistics is determined by mutual statistics. It's not true for even fusion order, but for odd fusion order it is. So in that case, you're not throwing anything away. But anyway, there are two ways to repackage this information. One way is to define what we would call a Hermitian form, which takes values in Laurent polynomials, and it's given in terms of little b. And the formula is not so important. The physics of this expression is that this big B object, it keeps track of the mutual statistics between x and y, but also all the relative translates of x and y at the same time encoded in one polynomial. So the different coefficients of that polynomial are the statistics of all the relative translates of x and y. Okay? And there's a kind of complex conjugation operation here, which is just inverting the translations. And this is Hermitian with respect to that operation. There's a property that turns out to be very important, which is that we know B is non-degenerate, and that actually implies that S are fusion module is something called a torsion-free R module. And I wrote the definition here. That's not so important. It's just some property if you're not familiar with it. But it plays in a very important role in the theory. There's yet another way of repackaging the same information. So you take this bilinear form B, and you can turn it into a map from S to S dual, where S dual is a module of linear maps from S back to the ring. Okay. So this and this are completely equivalent. That's a quite general thing if you're familiar with bilinear forms. Yeah.
So I think before you said that inside the R module, all the sums have to be finite. And is this whole too as an infinite sum will be finite?
It is, because by this locality assumption, only finitely many of these terms are non-zero.
Okay.
That's what that comment means. Yeah, good. Okay, so it turns out, and it's a story that I won't have time to tell you, that there's also an obvious condition on the data. Meng, you can ask your question first.
So on the previous slide, the word injected, does it follow automatically from the assumption?
Yeah, injectivity is the same as non-degeneracy here.
non-degenerate. Okay,
Yeah,
okay.
it's the same. That's an easy thing to check. Yeah, so there's also a condition on this algebraic data which is not obvious. And it's kind of a long story where this comes from. And I'm not going to have time to tell that because I want to emphasize some newer results. But we proved a theorem which tells us that in order for one of these theories to be physically realizable, this map phi not only has to be injective, it also has to be surjective. So it has to be an isomorphism. And why is that true? So the condition that phi is an isomorphism is equivalent to a more physical condition that if we compactify the system to 2 dimensions, to a 2-dimensional system in the stacking direction, basically you can think of it like a big 2D enneon theory. Once you do that, then this condition is equivalent to all those compactifications to 2D being modular theories of abelian enneons. And that has to be true for all the compactifications larger than a certain size, okay? Because the non-modular theories are not realizable. And there's an example that shows that if you don't impose this extra condition, you can find a theory which has non-modular compactifications. It's also equivalent to something else, this excitation detector principle. And the way to think about these 3 properties is that number 1, this thing being an isomorphism, is kind of the property you want in your definition to actually work with. It's a good property to work with. Number 2 is really hard to work with, so it wasn't easy to prove this theorem, but it's a physical condition. And number 3 is something that's important as a new physical principle, which is something that should, we believe, hold more generally. So there's sort of an outcome of this part of the story, which is that we know what we believe what the algebraic theory of a planar-only Fracton order is. It's a pair S theta where this associated map has to be an isomorphism. Okay? And so to proceed, we'll always take the fusion order to be a prime power, p to the k, and we'll try to understand these theories, and that problem will be easier for small values of k, and it's going to get harder and more interesting as k increases. As I said, this module S is a finitely generated torsion-free R module over this ring. That's an important property. An important comment to make is that we don't know for sure yet that all of our theories S theta are actually physically realizable. I think this is true, but we don't know for sure. A good way to show this, since we're making progress with classification and getting nice results, is to classify first, find some generator of your classification, and then just check that your generators are realizable. That's a much easier thing to do than trying to show realizability in general in the abstract, which could be pretty hard. Okay, so now I want to tell you something about classification and characterization of these planar-only Fracton phases. And in order to do this, we have to talk about what we mean by phase equivalence, right? We have to say what our phases are, and when 2 of these algebraic structures should be thought of as the same, when they should not be thought of as the same. So here's where the role of translation symmetry comes in a really important way. If we just think about it in the usual way, if we just say, look, I want to think about translation invariant systems. Okay? Then what we should do is take our phases to be isometry classes. So any two theories are the same, equivalent, if there's an isomorphism from S to S prime that also preserves statistics. In this context, that would usually be called an isometry class. But there's this is very simple, but there's a problem with this, which is that we know that imposing translation in a strict way as a symmetry, as usual, introduces some extra phase information that we might not want. We don't want it at first. It would be the wrong way to organize our thinking. The examples that you can think about come from symmetry-enriched topological phases, where if you have the toric code with no symmetry, that's a phase, but if you add translation symmetry, there are multiple different phases that all become the same when you break the translation. So you could say, well, why not just break the translation? Fine. The problem is we need the translation to talk about mobility. Okay, and so there's a compromise. What do we do? Well, as an intermediate step, we can first talk about these translation invariant phases, the ones that we get sort of as usual, our isometry classes. And these form a nice algebraic structure that comes from stacking of physical systems, and it's something called a commutative monoid. This is just an abelian group without inverses. Okay? And that's a structure that you really want on any set of phases, because you want to ask what happens if you stack two systems, then what phase are you in? So here's our compromise, how to break some of the translation symmetry but not break it completely. And so in this context of planon-only fracton orders, what we want to do is combine two physical operations, and then we want to declare this system and this system to be equivalent under some equivalence relation. So what are the operations? So one of these I call coarsening, and it goes back to Ha, who called it coarse graining. And this is an operation where we just forget some of the translation symmetry, as represented by this longer red arrow. Now, that's not enough because we can't really compare this system and this system anymore. And it wouldn't mean anything to stack this and this together, because they have different units of translation. So we actually have to also do something else, which I'll call translation deformation. We just rescale the lattice in three-dimensional space, R3, and you can do that by rescaling how the translation symmetry acts. So all you're doing is just squeezing it to make all the layers close together. And we'll declare these two things to be equivalent. So this composite operation is something that we'll call deformation by M, and it acts on S in a nice way. You can understand what it does to our module of superselection sectors. And there's some technical comments here that I think I mostly want to skip. But the way that you actually define the equivalence relation is you take a translation invariant phase, you write it as a stack of two other phases, and you deform one of the summands. You might think, why do you do this step? Why not just deform it right away? If you do that, you wind up losing your binary stacking operation. You can't keep it. And this can actually be physically justified. It's sort of allowing deformation through certain quasi-periodic systems. And if we want to break translation symmetry anyway, why not do that? It's kind of the, we're trying to find like the nicest way that we can to impose as little translation symmetry as possible. And I'm telling you that that's what this is. Formally, it also corresponds to something nice in the category of monoids. A remark for a few people in the audience, it's a co-equalizer of a certain family of maps. So that tells you that when you do this, you also get, you get equivalence classes with a nice binary operation. So I'll call this deformable lattice phase equivalence, or sometimes coarse equivalence. Okay. Good. All right, so the resulting phases we'll call deformable lattice phases, or DL phases. They have some nice properties that I don't have time to talk about. If you want, you can also quotient out by the sort of boring decoupled layers to get something that you might call foliated DL phases. Okay, and this is something that you can also do just for fusion only, if you forget about the statistics, just for R modules. All right. So now let me kind of summarize some of our results by fusion order going higher. So we'll start at fusion order P. So now planar only Fracton orders with fusion order P, right? So in this case, the ring is just Laurent polynomials with ZP coefficients. This is a kind of ring called a principal ideal domain. PIDs have very nice properties. And it actually follows from this result, which is a standard result, I don't have time to explain, that our module S has the structure of decoupled layers. It's a free module over this ring. So fusion has to have the structure of decoupled layers here, but what about braiding? Okay. So it turns out, I'm going to skip these details because I want to get to something more interesting. It turns out that you can prove that the braiding also has to have the structure of decoupled layers. So if you look at the mutual statistics, you can show that it actually has to decouple between some way of organizing the layers. It's not an easy result. It took us a while to prove this, or rather maybe it didn't take Evan a long time to prove this, but it took me a long time to understand his proof, which was correct. Okay, but anyway, in the end, the answer is sort of boring, that all of the fusion order P theories are just decoupled layers. Okay. So, all right. So now I want to tell you something more interesting. So what happens at fusion order P squared? Okay. There's a certain structure in these in R modules at fusion order P to the K that we use. And what you do is you have a sequence of inclusions of submodules where M sub S is just everything that's annihilated by P to the S. Okay, and these sit inside each other. This is something called a filtration. And in a torsion-free R module, this filtration has some nice properties, and it lets us write down something that is kind of like a basis. And there's, in the sense that if you make a certain choice, any superselection sector can be written uniquely as a linear combination of these basis elements. That's kind of the key property. And I'll give an example. Okay. But the other important thing is that all of the fusion can be expressed in terms of these basis elements. And actually, all you need to know is what happens when you act with you take a basis element and you multiply it by P. And then you have to get a linear combination of basis elements that live at lower orders of this filtration. So here's a really simple example at fusion order P squared. There are just two basis elements, x1 and x2. And if you multiply x2 by P, you just get T minus 1 times the other basis element. And P times x1 is just 0. So this defines a module. It defines an R module. And we'll call this QSSC because the fusion module of this SSC theory is essentially just two copies of QSSC. Okay. All right. So now I get to some things that are more work in progress. I'll skip this because it's less interesting. And what I want to tell you about is an interesting mobility invariant. So I don't really have time I thought I would have time to describe this in a little bit more detail. But the point, now we're at fusion order P squared, okay? So this filtration only has two levels. What you can do, if you start, for example, with this module QSSC, is you can ask what happens when you just multiply everything by P, okay? All right? And so this gives you a map from the whole module to the submodule of fusion order P elements. And you can take a certain quotient. I have to skip some details here. But by basically studying this map multiplication by P, there's a way to extract a very finite object from this. It's actually just a finite dimensional vector space over the finite field Fp. And it has a physical interpretation. It's sort of telling you to what extent are there excitations of fusion order P that you can't get by fusing together higher order excitations. It's kind of measuring that extent. So this number is some integer, non-negative integer. If it's bigger, there's kind of more excitations at low fusion order that you can't get by fusing together higher order excitations. And if this number is 0, you can get everything by fusing together higher order excitations, essentially. Okay. This invariant, or this quantity d of m, it's 0 for decoupled layers, okay? It's 1 for this example QSSC I told you about, and it's additive, so it's 2 for SSC. And there's a theorem, which is that up to decoupled layers, this actually gives a complete invariant for these coarse equivalence classes of R modules. So it actually tells you everything that you might want to know if you're trying to classify planon-only fracton orders. Okay, and in the context of a planon-only fracton order, this is what we would call a mobility invariant, because it doesn't know about the statistics at all. It only cares about S. And I always thought it was kind of amazing that in these planon-only fracton orders, where everything is a planon, there is even an interesting mobility invariant. But there is one, okay? Okay, so how can we use this? All right, so now if we actually want to classify planon-only fracton orders, we need the braiding as well, okay? So there's a way to express the braiding as a matrix, which has a certain nice block form. Some of the blocks are 0, some of them are non-zero. What you can do is then you can conjugate this matrix with U and U dagger, where U is some invertible matrix, so that's called a congruence. It's really just a change of basis, so you can keep changing the basis. And after enough congruences, and after using this deformation, there's a theorem which is that the only thing you can get is a direct sum of braiding matrices for the SSC theory. So what this tells us is that every planon-only fracton order, up to decoupled layers, just a stack, every k equals 2 planon-only fracton order, is just a stack of SSC theory. So that's why it's such an important example, because it's the only example at fusion order p squared, essentially. Okay? And here's its braiding matrix. You can write it down. Okay? And in this case, you know, this mobility invariant d of s is actually a complete phase invariant. It tells you everything. So not only do we have a classification, we also have a full characterization where we have an invariant that uniquely labels every phase. All right. So the last thing that I'm going to have time to tell you about before we have to stop is to, as promised, I have to make a connection to subsystem symmetry. Okay. So the kind of symmetries that we want to consider are the simplest subsystem symmetries. So we just take a translation invariant family of parallel lattice planes, and our symmetry generators just have support on a finite number of planes. So one could look like this, another one could look like that, and the full symmetry is just given by taking products of these generators, maybe infinite products, and the translates of these generators. It was not known previously that these symmetries could be interesting, because all the known examples, I believe, are just products over decoupled layers, which is not that interesting. It's kind of like a decoupled layer fracton order. Okay. But what we can do, using things that we learned from thinking about planon-only fracton orders, is not try to think about the symmetry itself, but think about its charge module. Think about the charges carried by its excitations. So it's possible to argue that the charge module of the symmetry has to be a finitely generated torsion-free R module. Okay? But now, as I've told you, we know a lot about those R modules, and the approach is that we can characterize and classify these one-planar subsystem symmetries in terms of their charge modules. So what's the output of that? Well, at fusion order p, this charge module is a free module, and that corresponds to symmetry just being a product over decoupled layers, which is kind of boring. At fusion order p squared, after sufficient deformation, then our charge module has to be a direct sum of some number of copies of QSSC, ignoring decoupled layers. Okay, and in this case, this invariant d of q it's again a complete coarse invariant if we ignore decoupled layers, and it measures to what extent the symmetry is non-product-like. So I don't have time to tell you about this, but you can write down explicit symmetry operators for these symmetries, for any of them actually, which is important to convince yourself that you're not fooling yourself just by more abstractly studying their charge modules. You can gauge this symmetry and get the SSC theory as an untwisted gauge theory, which people who worked on it will find to be an interesting statement because it wasn't known how to do that before. But kind of the bottom line here is that, especially if you think about this more generally at higher fusion orders, there are a lot of interesting finitely generated torsion-free R modules. And at higher fusion orders, we don't know how to describe them all yet. And so therefore, there are a lot of interesting non-product-like one-planar subsystem symmetries. And so classifying these and characterizing them is definitely not a trivial problem. So we're out of time. So I'm going to go to some outlook. So there are more results that I didn't have time to show you. But kind of the bottom line is that these are kind of the first steps, I think, toward characterizing and classifying Fracton orders and subsystem symmetries. And there's a lot more to do. And one comment I want to make, actually, which you might wonder after listening to this talk, is that you could say, look, planar-only Fracton orders seem really simple. They're kind of like abelian anyons. Why are they a useful model at all? Well, there's some mathematical similarities that we're learning about. So we actually think that they are a useful model. I'm not going to explain these comments, I guess, because I don't really have time. But the point is that if you think about what kind of mathematical structure you get from a planar-only Fracton order in a more abstract way, what we've been learning in work in progress is that more general Fracton orders can be described as generalizations of that structure. So this is sort of thinking about this structure in the right way. It does seem to put us on the right track where we can start to describe more general things, like the X-cube model, and also even Haas code, and other more complicated Fracton orders. So that's where I think this is headed, and there's more to come in this direction. So thanks. Sorry for going a little over time.